Hi guys, we're going to take notes on hypothesis tests for the difference in two proportions. Okay, so what does that mean? Well, last time what we looked at is a hypothesis test with one proportion or one sample. Okay, this is technically chapter 22, and you can use your book and read through it if that helps you. So last time we were looking at some population. Let's call this our population. Let's say we're talking about CPS students. And what we did was we made this hypothesis about our population. So the hypothesis, let's say, is that the percent of students who are completing work outside of school during this coronavirus time is 75%. That's the hypothesis test. So the proportion of CPS students completing work right now is 75%. Now, what we do is what we're going to say is, okay, well, I don't think that's true. I'm going to take a sample out of this population, and I'm going to find a sample proportion for those that are completing work. And in my sample proportion, I find that 50% are doing work. So my sample is showing 50% are completing work. And so from this, I'm going to develop another hypothesis where I think, well, that is just too high. The true proportion of CPS students completing work is less than 75%. And that is what we did in the last guide. Pause the video and see if you can challenge yourself to come up with the steps for the hypothesis test after the hypotheses. Okay, so from the hypotheses, you would then check conditions to make sure that you could make a normal curve so that we could find probability. Then you make your normal curve because samples should show, for samples, should show that if this is true, that the percent who are completing is 75%, and we find the standard deviation for that. Let's say our sample size was 100 students, and we calculate that standard deviation. You make your normal curve, and then after your normal curve, you figure out the z-score for your sample. And then you find the probability of your sample occurring or less. So normal CDF to find your p-value. And the p-value was the probability that you could get your sample if HO is true. And so if your p-value is really, really low, we are like, well, it's impossible to get our sample if this is true. But we got our sample, so this must not be true. So then we decide if we reject HO or fail to reject HO, and we make our conclusion in context. All right, so in this next chapter, we're doing the exact same thing we did here, but instead of looking at one sample and one population, what we're going to be doing is comparing two populations. So this time, we're going to look at two different populations, and we're going to propose something about these populations. So let's say this is CPS students. I guess maybe we go with selective enrollment students versus Noble students. And we want to show that the percent of selective enrollments, what we're going to assume that they're the same. Percent that are completing work are the same. That's what we assume every time. They're the same. They must be the same. But it's possible that they're different, and so what we're going to show with RHA is a difference, and we can propose any difference we want. I might say that I think that selective enrollment is doing more work than Noble. And so what I'm going to do is I'm going to take a sample of selective enrollment kids and a sample of Noble kids and compare them. And so that's what we're doing in this chapter. So we're going to do a few examples. Actually, why don't we go ahead and do these examples? Let's say that I found that the selective enrollment kids, I took a sample of them, and I don't know, 60% of them were completing work. And then I took a sample of Noble kids, and I found that 50% of them were doing work. So with this, and let's say my sample for the selective enrollment schools was, I don't know, 100 kids, and my sample for Noble schools was, I don't know, it's easier to get Noble students, so I'm going to go with 200 kids. All right, so what we would do first, and what we're going to do first is we're going to just understand what our two populations are and label what we have, which I've kind of done already. I've labeled my p hat and my n. I've got my hypotheses done here, so that would be my next step. Just like we did up here, we would label and do our hypotheses. Our next step is to check our conditions. So what we're going to do is check conditions for each population here. So the first thing I'm going to do is I'm going to make sure that it's big enough for normal. So 100 times 0.6 is 60, which is bigger than 10. So it is big enough for normal. I'll do the same over here. So we know we can do that normal approximation. All right, so that's good. We also need to check that our samples were selected randomly, and we have to assume that. We have to make sure that they are independent, so my selective enrollment students are independent of my Noble students. They should be. And within the sample as well, we should also see independence. One student at a selective enrollment school shouldn't really affect another. And we also need to make sure that they're independent by the 10% rule. So our sample of 100 needs to be less than 10% of all selective enrollment students. That's true. And 200 is less than 10% of all Noble students. That's true too. So we are good to go with our normal curve. So what that means is we are going to make our normal curve. And now you might be asking, Miss Shine, what goes in the middle? Well, typically what went in the middle was the number in our hypotheses, right? And here, I don't have a number, but what I'm doing is I'm comparing selective enrollment to Noble. And so if I'm going to compare people, let's say like we compare heights. My height is 5'7", and I don't know, Leslie's height is 5 feet. And I compare our heights, and I am 7 inches taller. What did I do to compare our heights? I subtracted, right? Because in order to compare something, you're just subtracting. So when I look at these two values, if I'm saying they're the same, that the selective enrollment is the same as the Noble students, to compare them, I'm going to subtract. If they're equal, S minus N should be 0. And you can see that too if you just bring this over. If you subtract, these become 0. And so really what we see in our hypotheses is that it's equal to 0. I don't know if you can see that. Okay, so really in the center of our curve, we're expecting there to be no difference. So this is the curve of all of the differences. Okay, and then you might be saying, ugh, well then how am I supposed to find a standard deviation if I don't have a number to work with, if my number is 0? You can't have 0 standard deviation. You can't have 0 variation. You're right. So we're kind of stuck with dealing with our p-hats because we don't have any p's to deal with. So what we're going to be doing is we're going to assume that this is true, meaning we're going to put our p-hats together and make one pooled value, and it's called p-pool. So this is a new step, and that we have to find p-pool. Okay? P-pool is the success for your first population plus the successes for your second over n1 plus n2. So in this case, my successes, out of the 100 selective enrollment kids, 60% are doing work. So how many kids are doing work? Well, 60% of 100, 0.6 times 100 is 60. So 60% of 100 are doing work. Plus 50% of the 200 are doing work over 100 plus 200. Which is 53.533. So we have this p pooled, and so that becomes the number that we use for our standard deviation, except we have 2 different n's. So now what we have to do is do one for each n. So 0.533, 0.467 all over 100 plus times 0.467 all over 200. And this is our standard error. So it's not something that is as precise as you would for a 1 sample, but this is what we use for a 2 sample, is we find our p-pool, and that becomes our p and q, and then we put it over each n and add them. Okay, and so we type this in our calculator. And we get 0.061. So our standard deviation is 0.061, meaning we're going up and down by 0.061. And now we do exactly what we did up here. After we did our normal curve, we found our z-score for our sample. So here's my sample, and I'm going S to N, so I'm going to start with my S's and then look at my N's. And I see that the difference between my S and N, remember this is the differences. So we're looking at the differences, the curve of differences. So the difference between the selective enrollment and Noble is 0.1. So that's the difference that I'm looking at, which is kind of like right up in here, 0.1, 0.06, and 0.12. It's in between there. And so I'm looking at this 0.1 minus the center, 0, over the standard error, which we know is 0.061. And that gives me a z-score of 1.639. And then I go ahead and I do my normal CDF to find my p-value. So since my HA says greater than, I will normal CDF my 1.639 up to positive 999. And that will give me my p-value. .051. Whew. That's really close to 5%, but it's just over 5%. So since my p-value, so my conclusion will come here, since my p-value is over 5%, I have failed to reject HO. I don't have evidence to show the selective students are doing better or more. You're lucky. I was close, but no cigar. So again, it's the same steps. The only thing that changed is the way that we write our hypotheses, being that we're comparing the populations. So there's going to be two different P's. And the way that we set up our normal curve. The 0 goes in the middle, and we have to find this pooled value, and therefore this SE pool. Otherwise, a hypothesis test is the exact same as we did before. We're going to do one more example, and then that will be it for your notes on 2 proportion Z tests, 2 proportion hypothesis tests. So here, so here's an example. Would being part of a support group that meets regularly help people who are wearing the nicotine patch to quit smoking? The county health department tries an experiment using several hundred volunteers who are planning to use the patch to help them quit smoking. The subjects were randomly divided into 2 groups. Group 1 was given the patch and attended a weekly discussion with counselors and others trying to quit. Group 2 used the patch but didn't go to counseling. After 6 months, 46 of the 143 smokers in Group 1 and 30 of the 151 smokers in Group 2 had successfully stopped smoking. Do these results suggest that support groups could be an even more effective way to help people stop smoking? The first thing asked to do is to identify the 2 groups being compared and label all the relevant information. So we have Group 1, which is the counseling group, and we have Group 2, which is the no counseling. So those are our 2 groups, and now we're going to label our N's and our P hats. So our N for Group 1 is 143, and our P hat is 46 out of the 143. So if you need to, you can go back and reread the problem and again try to figure out what are these 2 groups that we're comparing. So it looks like the subjects were randomly divided into 2 groups, and so we know we have Group 1 given the patch and attended a weekly discussion with counselors. And Group 2 also got the patch but did not participate in counseling. So those are the 2 groups, counseling and no counseling. And then we look at the numbers that go with it. So for no counseling, there were 151, and 30 out of the 151 quit smoking. So this was 32%. And this is 19.9%. Okay, so what are we trying to show? We're asked, do these results suggest that support groups, so counseling, could be a more effective way to help people stop smoking? So we're trying to see that more stop smoking with counseling. So if these are 1s and these are 2s, I want to show that the percent in counseling in Group 1 is more than the percent in not counseling. Okay, and my HO is always going to be those 2 are equal. I have to assume they're the same until I can prove they're different. Okay, then I'm going to check conditions for each. In this case, I guess I'll do it. Okay, 143 times 0.322 and 143 times the Q of this would be 0.678. And those are both going to be bigger than 10. I know this is 46 because it's right here. I know that if I multiply these 2 together, I should get that top number. So this is like 93, no, 97. All right, so it's big enough for normal curve. And I'll check this side too. That's gonna be, those are both bigger than 10 as well. Okay, so if they're big enough for normal, they also need to be random. Well, we will assume that it's randomly assigned. Does it say randomly assigned? Randomly divided, it's stated. Stated that they were randomly assigned their treatment. And we can assume that they're independent as well. We don't really have to do the independence 10% check because it's not really a specific sample. It's these people who are part of the experiment. They didn't do like sampling from a population. So in that case, it shouldn't really matter. So we're not going to do the 10%, but we can assume independence. So independent samples. All right, now here are the two new steps, finding p-pool and finding SE pool. So we have to assume in order to make our curve, we need to be able to find the variation. We know in the middle is 0, but we need to find the variation, and we know that we don't really have any numbers with our HO. So we have to use these sample proportions to make our p-pool. So we use the successes, which are actually given to us right here. And you can also find them in your conditions check. Okay, so the success for group 1 plus the success for group 2 over the n for group 1 plus the n for group 2. And you can multiply. If you do 143 times 0.322, like 32% of the 143 were successes, you get that 46. So you can also multiply if you want. And then when you combine them, you get 0.259. All right, so with that P pool, you can then find your SE pool by using this as your P, and therefore your Q is this over N, and then doing so for the other N as well. And combining them to get .051. So we're going up and down by 0.051. Okay, and up by that as well. Okay, so when we find our z-score, we do that for r samples. So we look at the difference in r samples. This goes 1 and then 2, so we'll do P1 minus P2. So 0.322 minus 0.199. That's the difference for r samples. We did 1 minus 2, and then we subtract by the center, which is always going to be 0, but we still put it there, and then divide by the standard deviation. And we get 2.411. So somewhere out here, 2.4. Somewhere out there, 2.4. All right, and then we find our p-value. So that means we need to find the probability of being at 2.411 or higher. So 2.411 to positive 999. And we don't need to multiply by 2 because we only want this upper tail. If this said not equal to, we would take this and we would also want the lower tail. So we would want double that value. But we only want this upper tail, so it's just 0.07795. And since our p-value is less than 5%, we reject HO and have evidence to show counseling works. All right, and that's it. Good luck.